Good morning to you all. Today we are going to study principles behind flotation. Okay. Today we are going to learn about flotation. Okay. In our day-to-day life, we have observed that some objects like wood, plastic, etc. are float on water. Okay. In our day-to-day life, we observe these scenarios. Some objects are floating on the water, while objects like stones, iron ball, rocks like objects are sink in water. Okay? We observe in our day-to-day life these scenarios. That is, some objects are float on water, while others are sink on water. What's the reason for this difference? Okay, what's the reason some objects are floating while others are sinking? So now let's be study what's the scientific reason behind these scenarios. Okay, we are going to learn the scientific reasons for these scenarios. Okay, there are many instances. Okay, there are many instances where we feel there was a force exerted by water upward. Okay, in many instances, we can say number one examples. When a bucket of water is immersed in a water, it appears lighter. Okay, when a bucket of water immersed in water, it appears lighter. But when we take it out of water, it appears heavier. Okay, these we have experienced in our day-to-day life. Okay, second example is when we swim in a pool. Okay, if we swim in a swimming pool, we feel we are lighter, but when we come out, these feel we have more weight. Okay, these all occurrences are due to the upward force exerted by water. Okay, by these instances, there are many instances we can say. Here I have mentioned only two instances. When we immerse a bucket of water in water, it appears lighter than we take it out from the water. Likewise, when we swim in the swimming pool, we feel we are lighter than when we come out. From these occurrences or these happening, we feel there was a force must be exerted by the water, that is upward force. Okay. From these observation, we can say there was an upward force. Okay, there was an upward force exerted by the water. Okay, from this observation only we can't say there was a upward force exerted by the water. So we have to confirm it scientifically. Okay, so we have to confirm it scientifically. So let's carry out this activity to find out there was an upward force is exerted by the liquid. Okay, to find out there was an upward force exerted by water, we will carry out this following activity. Okay, to do this activity, we have to take spring balance and piece of metal as well as a beaker with water. Okay, we have to take these three objects. First, we have to tie the piece of metal, or we have to sustain this piece of metal with spring balance. Okay, first we have to suspend this piece of metal and spring balance, and we get the reading of Newton balance. We may assume it as A. Okay, first we suspend a piece of metal with string balance, and at that time we get the Newton balance reading as A. Okay, this is here. There was a weight Force of train is exert in downward direction. So, as per the Newton third law, there's an each and every action there's an equal and opposite direction. So, the object is a rest state. We can see when we suspend a piece of metal with spring balance, the object is at rest. So, the resultant force is 0. If there is a resultant force, as per the Newton's second law, if there is a resultant force is available, there should be an acceleration. So, object will move. But here, the object is at rest state. So, as per the Newton's third law, the upward there was an upward force, mg is acted downward, so the tension T is acted only upward. So in this instance mg is equal to T. Okay, T, that is tension. So Newton balance reading in this scenario is A, we have taken. Okay, thereafter we have to apply the upward force. Okay, here we are going to apply the upward force by our palm. Okay, by our palm, by our fingers, we apply a upward force on the piece of metal. Okay, now we get the Newton balance reading. It's we assume it's as B. In these scenarios, we can observe the Newton balance reading at A is greater than Newton balance reading at C. Newton balance reading at A greater than Newton balance reading at C. Okay, that is B. So, from this observation, we can say if there is an upward force acts on the object that is hung on the spring balance or Newton balance, the Newton balance reading will reduce by this upward force. Okay, we can confirm that if there is an upward force exerted on the piece of metal that is hang on spring balance, the Newton balance reading will reduce by the force that is applied by us upwardly. Okay, so from this observation we can confirm if we apply a upward force, the Newton balance reading will reduce. What's the reason for the reducing this Newton balance reading? Now, if we look this object, the the weight of this object acts in downwardly, and we apply a upward force that is set. So now resultant force of this instance is mg minus F. Okay, this is the resultant force. As per the Newton's third law, the object is at rest. Okay, so the T should be equal to mg minus F. Okay, the object is rest, so we can say the upward force is equal to downward force. So in this instance, the Newton balance reading is mg minus F. So the Newton balance reading will reduce if we apply an upward force on the object that is hang on the Newton balance. Okay, we are going to use this principle in the T. Okay, instance T. Thereafter, we are going to immerse this piece of metal in the water. Okay, water bath. This is the water bath. We are going to immerse this piece of metal into the water. Now, we can observe that the Newton balance reading, we assume it as C. Newton balance reading is less than the A. Okay, we can observe that the Newton balance reading C also less than C. So, from this observation, we can confirm that there was an upward force must be applied by the water on the piece of metal. Okay, I clear? In the instance C, we get the Newton balance reading that is less than the instant same. That is very linear. Okay. So from this observation, we can confirm that there was an upward force exerted by the water on the piece of metal. Okay. So we can conclude when an object is immersed in a liquid that experiences upward thrust exerted by the liquid. Okay, when an object is immersed in water, there was an upward thrust or upward force is exerted by the liquid on the object. Okay, we can confirm this. Next, we will move to the next we will move to the forces acting on a floating object. Okay, here let's see what are the forces acting on the object that is in floating. Okay, first instance we see the object is submerged in a water. Okay, uh, the weight of the object, as already know, the weight of objects acts downward. That is, weight of object acts downward, and upthrust will act on upward. Okay, the upthrust will act on downward. Okay, so if an object is at rest, if we immersed an object within the liquid. Okay, if we immerse this object in a liquid, after this object being in rest, we can say there was, if the object is rest, we can say the resultant force acting on this object, resultant force acting on this object is zero, since there is no acceleration or there is no motion. So the resultant force acting on this point is zero. So we can say at that point mv is equal to 2. Okay. If the object, if after immersing this object, if the object move downward, okay, if there is any movement in downward, we can say object is moving in downward. So the resultant force should be act downwards. Okay, resultant force should be act in downward. So in this instance, we can say weight of the object is greater than 2. Since downward force is greater than the upward force. So we can say mg is greater than 2. Okay. Third instance, if the object move upward, we can say the resultant force should be upward. Okay, clear? The resultant force should be upward. So the upward force is upthrust. So 2 should be greater than magnesium. Okay. Upthrust, if the upthrust is greater than weight, the object moves in upward. And if the upward thrust is equal to weight, the object is uh, floating as submerged, fully submerged. The object is floating as fully submerged. Okay, but these objects will sink. Okay, still will sink, and this object, the third object, will float. These are the instances. Okay, so the forces acting on the floating object, if there is a there are two objects acting on a floating object. Those are weight of the object, that is mg, is act in downward direction, and also the upthrust. Upthrust is exerted by the liquid. So this act on the upward. When the object is floating as fully submerged, okay, that's important. If the object is floating as fully submerged, at that condition, mg is equal to upthrust. Weight is equal to upthrust. Okay. Next, we will see what is the real weight and apparent weight. Okay. There are two terms we are going to use, that is real weight and apparent weight. Actually, the real weight is the gravitational force of the acting on the object. Okay, the real weight is that is gravitational force acting on the object is the real weight. But the apparent weight is the weight source on the reading of scale. Okay, the apparent weight is the weight source on the Newton balance. Okay, this is the apparent weight. This is the real weight. Okay, real weight. This is real weight. That is the gravitational force acting on the object. That is m into g. That is the real weight. But apparent weight is the weight that is noted in the Newton balance. That is the Newton balance reading is the apparent weight. Okay, idea. First, if you see this object, first we weigh the stone in air. We get the weight as 0.67 Newton. So we can say the real weight of the object, real weight of object is equal to 0.67 Newton. Okay, real weight is 0.67 Newton. But in second instance, the Newton balance reading is 0.4 Newton. Why this reduction of this? We know when we immersed object in the liquids, there will be upward force will be exerted. There will be upward force exerted. That is 2. So the resultant force or the apparent weight will reduce. So apparent weight is the 0.4 newtons. Okay. So from this we can say the apparent weight is equal to, okay, apparent weight is equal to, this is the apparent weight, this is equal to weight of the object minus upward force exerted by the object, that is upthrust. Okay, that is the weight minus upthrust. Okay, the apparent weight is equal to weight of the object minus upthrust. Okay, we can say it as apparent weight is equal to weight of the object minus upthrust. Okay. Okay, now we have to confirm that there was an upward force is exerted by the liquid. Okay, when an object is immersed in a water, there is an upward force is acted. But we have to find the volume or the amount of this upward force. Okay, so to find out the magnitude, okay, the magnitude or value of the upward force or upward thrust, we have to carry out this activity. Okay, the aim of this activity is to find out the magnitude of the upthrust. Okay, upward force magnitude, the value of the upthrust we have to find out. This is the, so we have to carry out this activity. For this activity, first we have to take the Eureka vessels. This vessel is called as Eureka vessel. Eureka tank or Eureka vessel. Eureka vessel. This is Newton balance, and we have to take metal tube as well as this beaker. Okay, these are the things we have to take. First, we have to make a line in the metal tube as divide this metal tube into equal parts. So we have to take a line in the middle of the metal tube to divide this metal tube as two equal parts. Okay, then hand this metal tube in Newton balance and get the reading. Okay, in first instance, we just hand the metal tube in Newton balance and get the readings. Okay, we assume it as A. Okay, we get the reading at A. Thereafter, we have to immerse this metal cube up to the mark point. Okay, we have already marked now. Up to the mark point, we have to immerse this metal cube into the liquids. Okay, at that point also we have to get the Newton balance reading as well as the weight of the beaker. If we assume weight of the beaker is M, the weight of beaker plus water is equal to this is M1, that is weight of beaker. M2 is weight of beaker with liquid. Okay, we assume it as. Okay, thereafter we have to immerse the metal cube fully in the liquid and get the Newton balance reading. We will assume it as C and we get the beaker weight with water and we assume it as N3. Okay. Then fourth one, uh, we fully immerse this metal cube and get the reading. We will assume it as P and then weight of this water plus beaker as N4. Okay, unclear. What are the activities for we to confirm the weight or magnitude of the thrust? We are going to do this activity. Okay, for this activity, first we have to take a metal cube. Okay, metal cube. Then we have to mark a line in the metal cube as it has divided the metal cube into two parts. Okay, then hang this metal cube on the Newton balance and get the Newton balance reading. Okay, this is the first one. Second one, immerse this metal cube into the water up to the mark line. Okay, we have already marked now up to the up to line. We have immersed this metal and get the Newton balance reading. At the time we already studied the liquids can't compress. Okay, we have studied the liquids we can't compress. So, if any volume of object is immersed in water, that volume of water will displace. Okay, this is the fact. We have already studied. As per the fact, the water molecules can't compress. So, if we insert a volume of another objects into the water, that volume of water will displaced. Okay, according to the fact, when we immersed a part of metal cube, some of water will displaced. Okay, the volume of displaced water is equal to volume of this metal cube. Okay, we can say that this volume is equal to this volume since we have already studied liquids can't compress. So when we insert any object, that volume of water have to be displaced. Okay, that's the second instance. Then third instance, we immerse this metal cube fully as in the uh, uh, diagram C. Okay, fully and get the reading. Thereafter, fully immerse this metal cube in water and get reading. Okay, if we assume these are the reading we have taken, that is when reading at the metal cube reading near the water surface. Okay, that is near the water surface. There was no near the water surface. At the time this reading is the at the water surface. So there was no upward thrust acting on it. So we can say that is the weight of, that is the real weight of the object. Okay, metal cube near the water surface. Okay, only upward thrust is exerted only if the object is immersed into the water. Okay, so in the near the water surface, so we can say it as mg, that is the real weight of object. That is as 1.2 Newton is given. Okay, weight of beaker with displaced water. At this instance, we say when the metal tube is at the near the water surface, there will be no water displaced. Okay, there is no water displaced. So we can say it is the weight of beaker. Okay, we can say 1.3 is the weight of beaker. I clear? This is the weight of beaker. Okay, now second, at the instance B, when we immerse the metal tube as half submerged in water. Okay, as half submerged in water, the spring balance reading becomes 0.9. Okay, the 1.2 reduced by 0.9. This is the apparent weight. Okay, this is the real weight. This is the apparent weight. So we we already studied that the apparent weight is equal to, that is apparent weight is equal to real weight of object, real weight of object, real weight of object minus upthrust. Okay, we have already studied. So apparent weight is given as 0.9. We find already the real weight of the object as 1.2. So upthrust become as 0.3 Newton. Okay. By this spring balance reading, we can say the upthrust or upward force acted by the water is 0.3 Newton at this instance. Okay. That is 0.3 Newton is the upthrust. Upthrust. At first instance, upthrust is equal, and second instance, upthrust is equal to 0.3 Newton. Likewise, in the when metal tube fully immersed in water, okay, first half submerged, here fully immersed in water, the apparent weight become as 0.6. So the upthrust is equal to real weight minus 1.2 minus 0.6. So the upthrust become as 0.6 Newton. Okay, I clear? 0.6 Newton. And final instance, Q fully immersed. Okay, fully immersed in water and far from the water surface. Is fully immersed, like both are same, fully immersed, but it is near the water surface, but it's far from the water surface. So the upthrust become as 0.1.2 minus 0.6. So upthrust become as 0.6 Newton. Okay. Now we see the what is the weight of beaker with displaced water. Okay. First instance, there was no water displaced, so the weight of displaced water is 0. So weight of the beaker is 1.3. Okay, then we submerge the metal tube in water half submerge the metal tube in water. The weight of beaker with displaced water is 1.6. Okay, 1.6. We already find the weight of beaker is 1.3. So weight of displaced water is 1.6 minus 1.3. It becomes as 0.3 Newton. 0.3 Newton. This is the weight of displaced water. Weight of displaced water. Okay, this is the weight of displaced water. First instance, weight of displaced water 0. Since there is no water displaced. Second instance, when metal tube halfly submerged in water, the weight of displaced water is 0.3 Newton. And when the metal tube fully immersed, the weight of beaker with displaced water is 1.9. So we have to reduce the weight of beaker, that is 1.3. So 1.9 minus 1.3 becomes as 0.6 Newton. Okay. For last instance also 1.9 minus 1.3, so it's 0.6 Newton. Okay, from this activity we can observe that the upthrust acting on the object, first instance upthrust acting on object is 0.3 Newton, and also the weight of displaced water also 0.3 Newton. In second instance also same 0.6 Newton upthrust, and also the weight of water displaced by the water is 0.6 Newton, and third instance also same. So from this activity we can say the upthrust acting on the object that is immersed fully or partially in a water, the upthrust exerted on the object by the liquid is equal to weight of the displaced water. We can say this is the upthrust or upward force exerted by water. This is equal to the weight of displaced water 0.3, 0.3. So from this observation we can confirm that when the object is fully or partially immersed, that is the important. If, if not immersed in water, there is no upthrust is exerted. Okay. So the object have to immersed in water partially or fully. For when the object is immersed in water partially or fully, the upthrust acting on the object is equal to weight of the volume or weight of the water displaced by the object. Okay, weight of the displaced water. So now we find the uh, we can come to this conclusion. Okay, when the object is partially or fully submerged in water, upward thrust acting on the object is equal to the weight of displaced water. Okay, displaced water. This is the Archimedes principles. Okay, this was first discovered by the scientist called Archimedes. When we see the principle of Archimedes, when an object is partially or completely submerged in a fluid. We know fluid is the term we can use for the liquid as well as I already studied. No, we have already studied that the fluid is the term we can use for the liquid as well as gases. Okay, so if an object is partially or completely submerged in a fluid, the upthrust or upward force acting on it is equal to the weight of the weight of the fluid displaced by the object. Okay, this one we have confirmed our from by activities. Okay, now we move to the here there's an image that shows how three objects submerged in water. Okay, there are three objects, that is A, B and C. Here we see these three objects are floating in water differently. A is floating as partially submerged. Only this part is submerged. So A is floating as partially submerged and B is floating as fully submerged and C is sunk. Okay, C already sunk under the water. Okay, let's we study what are the reason for this difference. Okay, so we have to study what are the reasons for these differences. Okay, to find out the reasons for floating and sinking. Okay, some objects are floating while others are sinking. So we have to find out what's the reason for these different scenarios of the objects. Okay, for this activity, we have to take three objects, that is A, B and C. Three objects have different scenarios. That A has to be immersed as partially submerged. A has to be float as partially submerged and B has to be float as fully submerged and C has to be sunk. So we have to take three objects and hang these three objects on Newton balance. So we can get the weight of object, that is weight of object A is 1.1 Newton and 1.8 Newton B, and C is 2.4 Newton. That is the real weight of three objects. Okay. The real weight of object A is 1.1 Newton. Object B is 1.8 Newton. Object C is 2.4 Newton. Okay. Thereafter, we have to immerse these objects A, B, and C into the water. Okay. After the equilibrium, we have to get the weight of Newton balance. And that is we called as apparent weight. Okay. Apparent weight of A is 0. Okay. Apparent weight of B also 0. And apparent weight of C. That's the Newton balance reading when we take after the equilibrium of that objects in the water. Okay. The apparent weight of object A is 0. That means we already studied apparent weight is equal to weight minus earth thrust. Okay, apparent weight is equal to weight minus earth thrust. If the apparent weight is 0, that become empty, that is weight is equal to earth thrust. Okay, if the apparent weight is 0, that means the uh, downward force of the object, that is the weight of object, is equal to upward force of thrust. Okay, we can say at the point A, we can say the weight is equal to earth thrust. Okay, likewise in B also the apparent weight is 0. That means the downward force minus up thrust is equal to 0. So weight is become an equal to up thrust. Okay. And third scenarios, the weight of object is 2.4, but the apparent weight of object is 0.5. So okay, the up thrust of A is equal to 1.1 Newton. Up thrust of B is equal to 1.8 Newton, and up thrust in the scenario C, up thrust is equal to we have already studied the apparent weight is equal to weight of object minus up thrust. So up thrust is equal to weight of object minus apparent weight. Okay. So up thrust is equal in third instance. Weight is given as 2.4. Okay, 2.4 minus up thrust is 0. Sorry, apparent weight is 0.5. Okay. So up thrust becomes 1.9 Newton. Okay, 1.9 Newton. We can observe, if we see the object A, here the weight is 1.1 Newton, up thrust also 1.1 Newton. So object is floating. Okay, object is floating. There's no resultant force. So object is floating. And observe the instance 2. Here also weight of the object is 1.1 Newton. Up thrust is also 1.1 Newton. So the object is also floating as fully submerged. Okay, is also floating as fully submerged. When we see the instance C, here weight of object is 2.4, but the weight of object is 2.4, but up thrust is 1.9 Newton. So the weight of object is greater than the up thrust. So there was a downward force acted on this. So the object going to sunk. Okay, that's the reason for these different scenarios of these objects. Okay, from this activity we can confirm if the upthrust acting on an object fully immersed in a fluid, okay, fully immersed in a fluid is less than, if first instance if the upthrust less than the weight of the object will sink in the fluid. Okay, that is weight greater than the upthrust, the object will sink in the fluid. That is the first conclusion we have taken. And second conclusion, if the weight of object is equal to the upthrust, the object will, if upthrust is equal to mg, the object will float in the fluid by being fully submerged. Okay. If the object is floating as fully submerged, we can say upthrust is equal to weight of the object. Okay. If the weight of the object, okay, if the weight of the object less than the upthrust, if the weight of the object less than the upthrust, the object will float. Okay. If the weight is equal to upthrust, the object fully as being fully submerged. Okay. In second instance, object fully float as fully submerged. That is this, like this. The object is floating, but it's as fully submerged. But in the instance C, the object object will float on the water. Since the upward force acting on the water is greater than weight of the objects. So that in upthrust equal to the weight of the objects act on it. Okay. So these are the three instances. Okay. If the upthrust greater than weight of the object will float on water. Okay. Second instance, if the upthrust equal to weight of the water, object will float as fully submerged. Okay. As fully submerged. And third instance, if the weight of the object is greater than the upthrust, object will sink. Okay, now let's do some activity exercises. The weight of a piece of metal in air is 20 Newton. That is the real weight of metal is given as 20 Newton. Okay, when it is completely immersed in water, the apparent weight is 5 Newton. Okay, there are two facts given. That is, real weight of object is 20 Newton and the apparent weight is 5 Newton. First question is what is the upward thrust exerted on the piece of metal by water? Okay, we have studied upthrust is equal to weight, that is real weight of object, real weight or true weight minus apparent weight. Okay. Apparent weight. Okay. Real weight is given as 20 Newton. Apparent weight is given as 5 Newton. So we can say the upthrust is equal to 15 Newton. Okay. Second question. What is the weight of water displaced? Okay. What is the weight of water displaced by the piece of metal when it completely immersed in volume in water? So okay. When it completely immersed in water, we have studied Archimedes principle. That is, when an object is immersed partially or completely in the water, the upthrust is equal to, that is the upward force exerted by the object is equal to weight of the displaced water. Okay, we have already found that is upthrust is equal to 15 Newton. So, as per the Archimedes principle, the weight of water, displaced water, we can also weight of displaced water also water is equal to 15 Newton. That is the Archimedes principle. Okay. That's the upthrust is equal to weight of displaced water. So we can say it as 15 Newton. Okay. Now second exercise, that is what is the weight of the object? That is the real weight. Okay. We already know that real weight of object is the gravitational force of the object. When it hang the object in the Newton balance, the Newton balance in the air, the Newton balance reading in the air is called as real weight. Okay. So, what is the weight of object? At that point here it is given as 0.67 Newton. So we can say but the weight of the object is at 0.67 Newton. Okay, second question, find the mass of object. We have already studied that the weight is equal to mass into gravitational acceleration. Okay, mass into gravitational acceleration. Here, weight we have already find, that is 0.67 Newton. Mass is R, so M into G is 10. So M become as 0.067 kilogram. Okay. Find the mass of the object is equal to 0.6067 kilogram. Third question, what is the uh, displaced volume of water? Okay, third question asks, what is the displaced volume of water? Here the volume of displaced volume is given as 0.02 meter cube. Okay, that is the fact. What is the displaced volume of water? That is 0.02 meter cube. Fourth question, find the volume of object. Okay, as the fact the fluids can't compress, the volume of displaced fluid is equal to volume of object. Okay, as the fact the fluid or liquids can't compress. Okay, can't compress. Volume of displaced fluid is equal to volume of object. So, what is the find the volume of object? We can say it as 0.02 meter cube. Okay. Next question. What is the apparent weight of object? We already studied. Apparent weight is the Newton balance reading of the object. Here the apparent weight is 0.4 Newton. Okay, 0.4 Newton. Next question. What is the weight of beaker? Okay, what is the weight of beaker? Here noted as weight of beaker as 0.1 Newton and weight of beaker with water is here 0.37. So, what is the weight of beaker? That is 0.1 Newton. That is the fact given. Final question, find the upthrust. Okay, find the upthrust. We can find this upthrust in two ways. By this Newton balance reading, we can say the upthrust is equal to real weight minus apparent weight. Okay, real weight is given as 0.67 Newton minus apparent weight is given as 0.4 Newton. 0.4 Newton. So, upthrust become as 0.27 Newton. Okay. And another way we can calculate the upthrust is, we already studied that the Archimedes principle, upthrust is equal to weight of the displaced water. Okay, that is the weight of displaced water. As per the Archimedes principle, upthrust is equal to displaced weight of displaced water. Okay, so uh, weight of displaced water here, weight of displaced water with beaker is 0.37, weight of beaker is 0.1. So weight of displaced water is 0.37 minus 0.1. So 0.27. 7 Newton. So, in both instances, we get the same answer. So, upthrust we can calculate by two ways. That is, upthrust is equal to real weight minus apparent weight of object, or by the Archimedes principle, by the weight of displaced water, we can calculate the upthrust. Okay. Then there's an MCQ question, that is, consider the diagram given. What is the reading on the spring balance when the metal block is immersed in water. Okay, they are asking apparent weight. Okay, they are asking the apparent weight, that is the Newton balance reading they ask. Okay, here the real weight is given as 6 Newton. The real weight is given as 6 Newton. So the weight of object is 6 Newton. Weight of object is given as 6 Newton. Here another fact here given is displaced weight of water displaced. Okay. By the Archimedes principle, the weight of displaced water is equal to upthrust. Okay. So upthrust, we can say upthrust is equal to 2 Newton. Why? That due to the Archimedes principle, that's the upthrust is equal to weight of displaced water. So that is 2 Newton. So now we can say the apparent weight. Okay, apparent weight is weight of the object is the real weight minus upthrust is equal to, that is here, that is 6 Newton. The upward force is 2 Newton. So they asking this thing. Object is at equilibrium since object is at rest. So we can say T plus 2, that is upward force, is there's two upward forces, T plus 2 is equal to 6. So we can say T as 6 Newton. Okay, I will, sorry, 4 Newton. Sorry, 6 minus 2, that is 4 Newton. Okay, this is the answer. Now another exercise. There are two facts are given, that the apparent weight of object is given as 4 Newton, and also they are given the displaced volume of water, that is 100 centimeter cube. Okay, they are given only two facts, that is apparent weight, that is 4 Newton, and displaced volume. Here not, you have to consider this is volume, not the weight. Archimedes principle says the weight of displaced water is equal to upthrust, not volume. Okay, so first question, find the weight of displaced water. Okay, here also another fact given, the density of water is 1000 kilogram meter minus 3. Okay, volume is given, density is given. Okay, so we can find the mass, that is density is equal to mass upon volume. Okay, density is given as 1000 kilogram meter minus 3. Mass we have to find, volume given as 100 centimeter cube. So we have to convert into meter cube, that is 100 into 10 to the power minus 6. Okay, so M is equal to 1000 into 100 into 10 to the power minus 6. So these two become as 10 to the power 5. This is 10 to the power minus 6. So answer is 0.1 kilogram. This is the mass. Okay. But our question is weight. So we have to multiply this mass into gravitational acceleration, that is 0.1 into 10. It becomes as 1 Newton. Okay. Find the weight of displaced water. It becomes as 1 Newton. Okay. Next question, find the upthrust. Okay, find the upthrust. As per the Archimedes principle, weight of displaced water is equal to upthrust. Okay, so 1 Newton is equal to upthrust. So find the upthrust, that is also 1 Newton. Third question, what is the apparent weight of object? Apparent weight of object is a fact that was given, that is 4 Newton. And final question, find the mass of object. We have already found, that is 0.1 kilogram. Okay. Now we move to the hydrometer. Okay. Actually, hydrometer is an instrument, works under the principle of Archimedes. Okay. this hydrometer is used to measure the density of the solution and liquids. Okay, this hydrometer is used to measure the density of the solutions. Okay, actually this hydrometer is made up of glass stem, and there's a glass cylindrical stem and a bulb. Okay, within the bulb, there may be mercury or lead salts are found to keep this hydrometer upwardly. Okay, another instance we have to note the scale. Okay, when we see the scale of the hydrometer, in the upper part of the hydrometer, scale has lower value, that's maybe 1. But in the lower part, the scale may be 5 or 4. So we can say if the hydrometer immersed in a large volume in a liquid, we can say that liquid have low density. Okay, if hydrometer is immersed only a small depth, we can say the density of liquid is low. Sorry, no. But if the hydrometer immersed in large depth, we can say density of the liquid is low. Okay, these are the principle behind the hydrometer. Okay, in higher density liquids, hydrometer immersed only a small depth. Okay, while for the low density liquids, hydrometer immersed more. Okay, these are the facts. Okay, now we have studied the principle behind flotation. In our day-to-day life, we experience some objects are float, but while others are sink. So, what is the scientific reason behind these scenarios? So, we found that there was an upward force exerted by liquids when the object is immersed in a water. Okay. Thereafter, we calculate that the upward force of water by this activity. From this activity, we confirm that when the object is partially or fully submerged in water, the upward thrust acting on the object or upward force acting on the object is equal to the weight of displaced water. Okay, displaced water. That's weight of displaced water is equal to upthrust. That's the Archimedes principle we have studied. Uh, Thereafter, we have studied the instruments that works under the principle of flotations. That is Archimedes principle working under the Archimedes principles. Okay. This is the up to now we have studied hydrostatic pressure and its application. So these are the final topic of these headings. So thank you very much. We will study next unit in next class. Okay, thank you. Next class.